This integral is from the Harvard Math Qualifying Exam. One way to solve this is to start drawing semicircles in the complex plane for the residue theorem. It works, but today we are going to use Feynman's trick, differentiation under the integral sign, to transform this into a second-order linear differential equation. First, let me simplify the integral. We look at the integrand as a function of x. Replacing x with negative x gives us negative x times negative sine x, which simplifies back to our original function, f of x. Since it's an even function, we can integrate from 0 to infinity and double the result. One simple step, and we've already cut our work in half. This is where Feynman's trick begins. We introduce a parameter and call it a. We're going to evaluate this new function, L of a, instead. You might notice I added an extra x in the denominator. This isn't just for fun. It keeps the integral well-behaved when we start taking derivatives. The extra x will be canceled later during the differentiation process. Now let's differentiate L of a with respect to a. Taking the derivative pulls an x out of the sine function. The x in the numerator cancels with the extra x we added to the denominator. Differentiating a second time pulls out another x factor. The cosine becomes a negative sign, and we retrieve our target integrand. L double prime of a is the negative integral of our target. So our original integral I is simply negative 2 times L double prime at a equals 1. To solve for L, we need a way to link it back to that second derivative. We can use a partial fraction identity to split our main denominator. We apply this identity to the integrand of L of a. One part becomes the integral of sine ax over x, and the other becomes our target expression from earlier. The first term is a famous result called the Dirichlet integral. For any positive a, it's always exactly pi over 2. Substituting pi over 2 and our second derivative definition back into the equation gives us a direct relationship between L and L double prime. We just turned a calculus problem into a second-order linear differential equation. L double prime minus L equals negative pi over 2. To solve this, we look at the auxiliary equation. It's an elementary form with roots at plus and minus 1. The non-homogeneous part is just a constant, so the particular integral is simply pi over 2. Combining these gives us the general solution, a linear combination of exponentials plus our constant term. To find our constants, we look back at the integral definition of L of a. Setting a equals 0 makes the numerator vanish, so L of 0 is 0. What about large a? If we substitute u equals ax, the integral transforms into a form similar to the Dirichlet integral. As a goes to infinity, the term in the denominator approaches 1, and we're left with pi over 2. This confirms the integral stays bounded. Now we apply these to our general solution. An exponential growth term would violate our boundedness condition, so C1 must be 0. Substituting L of 0 equals 0 forces C2 to be negative pi over 2. We finally have our specific solution for L of a. Now we just plug a equals 1 back into our second derivative. We start with our formula for L of a. Differentiating once gives us L prime. Differentiating a second time gives us the L double prime we need. Evaluating at a equals 1, we get negative pi over 2e. Multiply that by negative 2, and we get the final answer, pi over e. No residues, no complex contours, just differentiation under the integral sign. If you enjoyed this derivation, like the video and subscribe to Matilda Academy for more. See you next time!